if g of x, y, z is a function of three variables, and S is a smooth surface in 3D space, then we're going to define an integral of g over S d, so with respect to the surface area differential, just like we generalized integrating over intervals to integrating over curves. So if g of x, y, z is the constant function 1, then this is recovering the surface area that we discussed in the last section. But if S were if we had some thin physical material, we could model by a surface, and G was the density of this material, so mass per unit area, then this would be computing the mass of S, or maybe slightly more precisely, the mass of the physical object, which is shaped like S. Okay, so let's write out the definition. So definition, we'll let G of X, Y, Z be a continuous function defined on a smooth surface S. Actually, we can take S to be piecewise smooth. So if S is not smooth, but S can be broken up into pieces which are smooth, then the integral that we'll define of integral g d sigma over S, this will just be the sum of the integrals over each of those smooth pieces. And I'll do an example of this. So in generality, we can work with things which are only piecewise smooth, but we can sort of reduce to considering only the case of smooth things. Okay, so the actual definition of this is done through sort of a limiting process, as we've done many times. Let's just get to sort of the actual formulas. So if S is given to us parametrically, by R uv, where for uv in some parameter domain R, then the integral of g over S is equal to the integral over R, g of R uv, so R uv is a point of S, and so we can evaluate g on it. And then d sigma, as before, is magnitude of Ru cross Rv, and then du dv. So next, if S is given to us implicitly, so S is all points x, y, z, such that f of x, y, z is c, so it's given to us as the level set of some function s, or f, then in this case, the integral over S of G d sigma, this is integral over R, haven't said what R is yet, G of X, Y, Z, and then d sigma again is gradient of F over gradient of F dot with some unit vector P dA. So here, P is a unit vector normal to a region R. Erase some of this. And we require that the gradient of F dot P is not equal to 0 for points where for points in S. So R, as before, will often be, like if we took P to be K here, then R would be contained in the XY plane. And in general, it's some plane region that we can project S onto in a one-to-one fashion. So R and P are like the same as what they were in the previous unit. And then finally, if S, so this isn't really a third case, it's a special case of both of the previous two cases. So if S is given explicitly to us as the graph of a function, Z is f of xy, for xy in some region R of the plane, then integral over S of G d sigma is integral over R G. So now Z is fxy, so it'll be G of x comma y comma fxy. And then we saw that the surface area differential here is given by square root of 1 plus fx squared. This is a partial with respect to x of f plus fy squared, and then dx dy. Let's clean this up. All right, so these are the formulas, and now we can sort of go off and calculate lots of things with these.